A very good morning to all of you. I hope that you've been enjoying the workshop so far, and a very, very warm welcome to day 4, session 5 of the WIO Regional Benthic Imagery workshop. My name is Dr. Alison Koch, and I'm a marine biologist at the Cape Research Centre of South African National Parks, where I work on marine protected areas. Please, before we get started, remember to choose your audio channel, English or French, and use the question and answer function to ask your questions to the presenter. If you like a question asked by someone else, please click the thumbs up icon. That way those questions can be prioritized. Please use the chat box for technical issues. Okay, so let's get started. We've got a jam-packed day today. This next session will include 3 presentations on baited remote underwater video camera sampling. And our first speaker is Dr. Anthony Bernard. Dr. Anthony Bernard is an instrument scientist at SIAB, the South African Institute for Aquatic Biodiversity. And his research is focused on understanding the ecology of subtidal reef ecosystems within South Africa, and the roles that natural disturbance, such as climate change and anthropogenic disturbances, such as fishing, play in shaping community and population structures. A large component of his research activity is also directed towards the selection and development of sampling methods to best survey fish and invertebrate populations associated with reefs, from shallow subtidal down to the deep sea. Anthony will be presenting his talk, and then this will be followed by a poll that he'll be running, and he'll also be showing a BRUV training video. After this, we'll then have his question and answer session. Anthony, over to you.
Hello, everyone, and thanks for taking the time to attend the BRUV session of this Benthic Imagery workshop. So my name is Anthony Bernard, and I'm a researcher based at the South African Institute for Aquatic Biodiversity, and we form part of South Africa's National Research Foundation. This presentation aims to provide information relevant to anyone interested in carrying out BRUVs and stereo-BRUVs research in the marine environment. The main focus is on stereo-BRUVs, but most of the information provided is also relevant to single-camera BRUVs research. This presentation covers 3 parts, starting with the description of BRUVs and stereo-BRUVs, and then providing a summary of how this method fits within the global marine research environment. We then go over the key design criteria and relevant standards before briefly covering stereo camera calibration. And then finally, we move on to what you need to conduct BRUVs research. This last part receives quite a bit of coverage in the training video that will follow this presentation, so we don't go into too much details here. The presentation does not cover image annotation and the detailed principles of sampling design, suitable statistical analyses, and detailed options for your data management, as these have or will be covered in the other presentations in the workshop. Furthermore, because the focus of this workshop is on benthic habitats, we haven't included a talk on the video analysis for the fishes. However, if anyone has questions, we'll happily assist as best we can. All right, so what is a BRUVs? For those who don't know, BRUV or BRUVs stands for Baited Remote Underwater Video System, and the S for system can be included or excluded depending on your preference. In its simplest form, a BRUV is a video camera in a waterproof housing attached to a frame with bait positioned within the camera's field of view. And this system can be suspended in the water column to sample the pelagic fishes, or more commonly put onto the sea floor where it records the benthic and demersal biota. Typically, the camera is positioned to provide a fixed horizontal perspective of the environment. The fixed camera position makes it easier to avoid recounting the same individuals when estimating abundance, and the horizontal perspective gives you a bigger field of view relative to a downwards perspective. This also lets you see the fish from the side, which makes identification easier. There are 2 main types of BRUVs that adhere to the basic standards: mono BRUVs, which use a single camera, and then stereo BRUVs, which use 2 cameras. In the literature, the term BRUVs typically refers to single camera systems that can provide data on species diversity and abundance. Stereo BRUVs, on the other hand, are BRUVs with 2 cameras that are positioned to provide an overlapping field of view or stereo vision, and when calibrated, these systems can provide accurate length measurements to accompany the diversity and abundance data. A distinguishing feature is that standard BRUVs are stationary and provide a fixed view of a portion of the sea floor. Setups that drift or swim transects should not be considered BRUVs, as the data won't be directly comparable. Similarly, Systems with rotating cameras likely do not provide comparable data. BRUVs and stereo BRUVs are now commonly used in most regions and marine ecosystems of the world to survey benthic and demersal fishes. The great thing about the methods is that they can be deployed in most habitats, from estuaries and intertidal ecosystems down into the deep sea and in fragile habitats or protected areas. As such, they have a great potential to provide standardized and comprehensive data to advance research and sustainable management. They have been identified by the Biology and Ecosystems Panel from the Global Ocean Observing System and the Marine Biodiversity Observation Network from the Group on Earth Observations as an integral method to monitor fish-related essential ocean variables and essential biodiversity variables. These standardized variables aim to support biodiversity management from local to global scales. To this end, there are currently efforts to establish a coordinated global observing program of independent researchers that collect and contribute standardized BRUVs data to global repositories such as OBIS and Global Archive. To achieve this, these programs rely on BRUVs research maintaining a minimum set of standards to ensure that the data are comparable and interoperable. As a first step, best practice guidelines have been published and are available on the Ocean Best Practice System. Much of what you will hear in this BRUV session can be found in the documents on OBPS, so I encourage you all to go and take a look. BRUVs are primarily used to collect data on fish assemblages. However, in doing this, they also provide a snapshot of the benthic environment in the field of view of the cameras. Using common approaches applied by benthic ecologists, this information can be quantified and analyzed to classify different habitat types. While these classifications are often used to help explain patterns in the observed fish data, they can also be used independently to investigate patterns in the macrobenthos and contribute towards benthic habitat mapping and the monitoring of essential biodiversity variables. Okay, so moving on to BRUV design. For both mono and stereo BRUVs, there's a wide variety of designs that have been developed over the last 20 years. And as long as you adhere to some key criteria that ensure that the data collected by the different systems are comparable, then there's considerable flexibility in how you build your BRUV. This is particularly true for the mono BRUVs, as you don't have to design the frame to maintain the stereo calibration of the cameras. Most design changes have aimed to reduce the cost, weight, and size of BRUVs and to increase their stability when on the seafloor. However, it's important to bear in mind that while smaller and lighter BRUVs will be easier to use, bigger and heavier BRUVs may provide greater stability and ultimately better data. A common issue with BRUVing is that the position the BRUV lands on the seafloor and the resulting perspective and field of view cannot be controlled by the researcher who's on the boat, and this provides scope for sampling artifacts to creep into the data if they're not accounted for. Ideally, you want the camera's field of view to include roughly equal amounts of seafloor and water column, as you're then able to detect both the benthic and demersal fish species. However, because most reefs are naturally variable in structure, with bumps, ledges, cracks, and crevices, the BRUVs often end up pointing up or down, and at worst falling over. This results in quite a bit of variability in the view of the reef habitat and can reduce the quality of the data. BRUV designs with rectangular bases are more prone to this variation because there's a greater chance that the base will land on a bump. However, if the BRUV has independent legs, or if it's based on a tripod design, then they are less prone to this source of variation. That being said, one advantage of the BRUV with the rectangular base is that there's more space to mount additional weights low down on the system, and this drops the center of gravity and makes it less prone to rolling over. Irrespective of the BRUV design that you use, it is good practice to quantify the field of view by measuring the extent of obstruction and the relative proportion of seafloor to water column within the camera's field of view, and these variables can then be used as covariates when you interpret the data. The second issue is that drag forces acting on the rope that connects the BRUVs to the buoys on the surface can result in the BRUVs being pulled onto its side or rolled over completely. Drag is caused by underwater surge, swell pulling on the buoys, or ocean currents as in this example. And this often results in the sample being discarded, as the data won't be comparable to samples that provide the horizontal perspective, and it's difficult to identify fish from their bellies. Some solutions to try and overcome this issue include increasing the weight of the BRUVs, lowering its center of gravity, widening its footprint, increasing the length of rope to reduce the lifting force, and reducing the rope thickness to reduce drag. However, if these don't work, then it's advisable to wait for the conditions to calm down before continuing sampling that area. A further challenge with BRUVs deals with underwater visibility and lighting. As BRUVs are a visual sensors technique, they rely on clean water. If the water is dirty, there's no real solution, and adding lighting doesn't really help. It's best to set a cutoff for the minimum acceptable visibility and only make use of samples that meet or exceed this criteria. We typically set a cutoff of 1.5 meters, so just past the end of the bait arm. Then for all your samples, it's important to obtain an estimate of underwater visibility for each BRUV's deployment. This measure can also be used as a covariate in the data analysis to account for differences between samples and locations. If the water is clean, but there's not enough light getting to the bottom, then artificial lighting does help, and the choice of light color and wavelength is important. Red light is supposed to cause the least disturbance, but it attenuates very quickly in water, so the illuminated area is not as big as what you would get with blue and to a lesser degree white lights. Blue wavelengths penetrates furthest in water. However, you have to be careful not to select a wavelength within the spectrum that makes fish fluoresce, as can be seen in the bottom two examples of the blue lighting. Other issues with blue and red lights is that you don't see the fish's natural colors, and this makes identification difficult, especially for small species. White lights are nice as they show the colors as we are used to seeing them, but they can attract plankton into the field of view of cameras. In general, both blue and white lights are commonly used in BRUV's research. So now that we've covered a few of the common issues related to the design, we can go into a bit more detail on the standard design criteria and features. It's important to bear in mind that many of these design features contribute towards the standardization of BRUV's data across different research groups and parts of the world. So first you have the frame that everything attaches to, and that provides protection to the cameras and stability to the BRUVs. As already mentioned, there are pros and cons to the different frame designs, and your end choice will be determined by your research environment, logistical capabilities, and budget. The base bar is then mounted within the frame at about 25 to 30 centimeters height off the bottom. The base bar is an integral component of a stereo BRUVs as it maintains the fixed position of the cameras and the calibration parameters. It is also the attachment point for the lights. As such, it needs to be sufficiently robust that it does not bend or twist when put under pressure. Typically, the camera housings are mounted to the base bar 70 centimeters apart with an inward convergence angle of 7 degrees to provide the overlapping field of view. This configuration lets you accurately measure fish up to 8 meters from the cameras. If desired, the camera housings can be closer, and 50 centimeter separation with 5-degree inward convergence angle is common, and this can help reduce the overall size and weight of the stereo BRUVs. However, it's important to note that the accuracy of length measurements decreases when the cameras are close together, especially when the fish are in the distance. The cameras should be at least high definition with 30 frames per second. Higher pixel and frame rates will improve the quality of the videos and make fish identification easier, but will also increase the amount of data that needs to be stored and managed. The other essential camera settings for stereo BRUVs are that image stabilization must be switched off, as this breaks down the stereo calibration, and then you want to restrict the horizontal field of view to roughly 95 degrees. A wider field of view results in the image distorting, and this reduces the accuracy of measurements. Nowadays, most BRUVs make use of action cameras, and the GoPro Hero Black editions have been proven reliable for stereo camera calibration. With the stereo BRUVs, the light can be mounted in between the cameras, and the light should aim to illuminate up to and beyond 3 meters in front of the system. As mentioned in the previous slide, blue and white lights are commonly used. Next, you have a 1 to 1.5 meter length bait arm that extends away from the camera, away from the frame, and holds the bait container in the field of view of the cameras. The bait container should hold 1 kilogram of crushed oily fish bait. Sardines or similar species are most commonly used, but if they're not available, then the most widely available bait that can be standardized should be selected. Bait containers can be made from PVC piping with end caps with numerous holes, about 10 to 15 millimeters in size, so that the bait can escape. Mesh bags are also commonly used. The frame should easily allow you to attach additional weights to improve the BRUV stability. This is true for all frame designs, and the lower the weight can be attached on the frame, the better. The rope used to connect the BRUVs to the buoys on the surface should float and have a breaking strain of about 1 to 2 tons, so that you can use force to pull the BRUVs free if it gets stuck. And then the rope length should be about 2 times the working depth. The surface marker buoys should be visible colors, and it's a good idea to mark them with relevant information to let people know that they are being used for research. Using 2 buoys connected by a short rope makes retrieval easier, as you can simply grab the connecting rope in between them. The required size of the buoys depends on the environment, and common sense should be applied. Strong current will easily pull small buoys underwater, and if you're working close to underwater cliffs, big buoys that can float the BRUVs if it falls off the cliff will reduce equipment loss. And then lastly, environmental sensors can be attached to the base bar. Useful information to collect include water temperature, depth, light, and oxygen. One of the most important design requirements for stereo BRUVs is that the position of the cameras relative to each other must not change during use. Prior to a research trip, the stereo BRUV is calibrated to enable the length measurements, and this calibration assumes that the camera parameters won't change. This means that the camera must fit tightly into a mounting within the housing. If you have to remove the camera from this mounting to change the batteries and SD cards, then it is essential that it is returned back into the exact same position. Alternatively, you can design the mounting so that you can access the battery and SD card while the camera remains attached. The cameras are often accessed via a cap to the underwater housing, and there should then be no variation in the alignment when the cap is reattached to the housing body. This can be achieved with alignment pins and guides. And then the housings need to be securely attached to the base bar, and the base bar itself must be rigid enough to eliminate any bending or twisting. You then need to ensure that the standard camera settings were used during the calibration, and that these settings are maintained for the duration of the research. And then lastly, you need to ensure that the cameras and housings are paired together. This is because individual cameras might have slightly different lens, sensor, or build parameters, which will influence the calibration. So by now you are aware that to enable accurate measurements, each stereo BRUV will need to be calibrated once it's been assembled and before you go into the field. And then again, upon completion of the field survey, each system will need to be recalibrated to account for any potential changes in the cameras or in the position of the cameras that might have occurred during the sampling program. And basically, the calibrations determine the 3D space within the area where the camera's fields of view overlap. Using this information, 3D coordinates or points on an object seen simultaneously in both the left and right cameras can be determined, and the distances between the points can be estimated. In this example, the points mark the head and tail of a fish, and the distances between them is its length. Cull and event measure are the most widely used hardware and software for stereo BRUV's calibration and the annotation of stereo BRUV's videos. Both software packages and the required hardware are provided by CGIS. While there are a few alternatives available, Cull was specifically designed for calibrating stereo BRUVs, making it fit for purpose and highly efficient. Furthermore, the output data files from the calibration procedure are easily read by event measure, which enables efficient and cost-effective point and stereo annotation of the videos. Both software packages undergo continual development to accommodate research needs, the latest standards in measurement of population parameters, and the technological developments associated with automated annotation of videos through artificial intelligence. The calibration procedure consists of two parts, with the first being in water, where you record a calibration cube and a measurement bar, and the second part of the calibration procedure uses the Cull software, with the videos recorded in the pool to implement a photogrammetric bundle adjustment that enables robust 3D measurement. Following this, the accuracy of the calibration is tested by estimating the size of the measurement bar in the event measure software and comparing it to its known size. For further information, the full calibration procedure is well documented in the software manuals. So once the calibrations and field surveys are complete, the output files from the Cull are imported into event measure during the video analysis, and the size of objects, a black mussel cracker fish in this case, can be determined by simply marking the edge of the tail and the nose in the left and right videos, and then the software calculates the size of the fish, which is 106 centimeters in this case. All right, so moving on to part 3. This section will mostly provide a high-level overview of what you need to conduct BRUVs and stereo BRUVs research, and we'll cover some of the requirements for your research plan and the equipment that you need, including the boat. Information is then provided on the short and long-term data management needs and options before ending with some requirements for video analysis. As with all ecological research, the employed sampling strategies must permit valid inference and interpretation of the resulting data. For the most part, stereo BRUVs research can be carried out according to widely accepted sampling designs. However, there are a few methodological requirements that must be adhered to. In addition, the selected sampling design will be determined by the goals and hypotheses of the project, the availability of suitable study sites, and the availability of resources. There's a rapidly growing literature of BRUVs and stereo BRUVs research, but in general, the research can be grouped into five widely accepted classes. A large amount of research has gone into investigating the optimal design for BRUVs and stereo BRUVs, and trying to get a better understanding of the strengths and weaknesses of the data in relation to more widely accepted methods. Baseline studies are used to conduct one-sort rapid surveys of previously undocumented areas. And then impact study designs, particularly where impacted sites are compared to control sites, are widely used to measure the effect of management interventions or fisheries on benthic ecosystems. And then there are a number of good examples of long-term monitoring programs which aim to investigate the trajectories of both natural and impacted populations through time. Lastly, research investigating ecological patterns and processes is also common, and there's a growing body of research looking into the intertidal as well as the deep sea ecology using BRUVs. So to look into some of the specific design considerations for BRUV research, firstly, an important consideration is random versus haphazard sampling. And this applies to most subtidal sampling methods, as in many situations, the absence of a detailed seafloor habitat map means that the habitat or population from which the samples would be drawn cannot be explicitly defined, and this precludes the use of randomized sampling. In this case, haphazard sampling is the only real option, with no scope for formal inference of patterns detected in the sample to the population. With BRUV's research, haphazard sampling usually entails moving to a randomly selected sampling location and then using the boat's echo sounder to look for suitable habitat at the time of sampling. However, if habitats or populations can be explicitly defined, then randomized sampling should be prioritized. Deciding if your research should be using BRUVs or stereo BRUVs will depend on the necessity for size data to address your research goal and hypotheses. Fish size is more sensitive to fishing impacts, so if the goals of the research are to determine the status of fish populations or the impacts of fisheries, then stereo BRUVs would be a better option. Furthermore, because habitat requirements of fish change with age and size, the size data provides valuable information to help interpret ecological patterns. Here it's important to note that BRUVs and stereo BRUVs most frequently use a conservative relative abundance measure called max-n. And max-n is defined as the total number of individuals of a species in a single video frame from the deployment. It is accepted that many more individuals of a species may be seen during the entire deployment, but because fish come in and out of view, you can't keep a cumulative tally without recounting some of the individuals multiple times. The deployment duration of BRUVs is also something to consider, and the standard deployment is 60 minutes for reef ecosystems. This is based on previous research and ensures that the maximum number of species will be detected at their maximum abundances. And then because BRUVs use bait to attract fish into the field of view, it is recommended that adjacent samples be separated by at least 400 meters to limit the chance of detecting the same individuals. This helps ensure the sample independence. All right, so onto the equipment. You'll need your BRUVs or stereo BRUVs, and ideally having multiple BRUVs will let you efficiently sample an area. If you are going to be using stereo BRUVs, then you'll need the calibration hardware and software. The calibrations are normally done at your home base so that you don't have to transport the cube in the field. But if you are going on an extended trip or to a remote location, then it's worthwhile taking it along to ensure your BRUVs are always calibrated. In addition to the cameras that are already in the BRUVs, you should always carry a couple of spares. Although the housings don't often flood, it does happen, and having spare cameras will ensure that you can always keep your BRUVs in the water. Depending on how many samples you plan to collect, you'll need batteries and SD cards for each camera on each deployment. Alternatively, you can set up your cameras with additional battery packs and large SD cards and keep them in for the full day. However, you do then run the risk of all your data if something happens to the SD card just before the end of the day. If you're using lights, then you'll need sufficient battery packs and some spare LED panels, again, to account for flooding if it happens. And then based on your research plan, you'll have a relatively good idea of the depth range that you'll be sampling. And you'll need to pack sufficient lengths of rope to allow sampling across the full depth range with all of your BRUV systems. So you'll need a set of buoys for each BRUV and again some spares. Importantly, depending on your research environment, you may need large buoys to reduce the risk of equipment loss. And then remember to write on the buoys to inform other seagoers that the buoy should not be tampered with. You'll need 1 kilogram of bait for each of your planned samples. It's best to keep it in a cool box for the day while at sea, so that if anything is left over, it can be refrozen and used on the next sea day. You'll then also need a way to crush the bait without making too much mess, and a sturdy bucket and wooden pole do an efficient job. A comprehensive toolkit to service the BRUVs and any electronics is also very useful. And then you'll need copies of your field data sheets to record all the relevant sample information for each BRUV's deployment. The research vessel is obviously an essential part of BRUVing, and medium-sized boats, so roughly 8 to 20 meters, are ideal as they are big enough to have davit arms and winches fitted and carry all the equipment, but are still maneuverable enough to ensure safe retrieval of your BRUVs. However, if you are working with small BRUV systems, then you can easily work off just about any safe seagoing boat. Very small stereo BRUVs can even be deployed off kayaks or walked into the shallow subtidal environments. If you have big and heavy stereo BRUVs or are working in deep water, then you will require a vessel with a davit arm or pot tipper and winch to safely deploy and retrieve the systems. BRUVing can be conducted off ships, but these ships must be maneuverable to ensure that they can hold their position above the BRUV during the retrieval process. With ships, it's also important to use stronger ropes, as if the BRUV is seriously snagged in reef and the ship moves over a swell while the rope is under tension, the rope can quite easily snap. And then besides being maneuverable and ideally having a winch and davit arm, every effort should be made to ensure that the vessel has a GPS-linked echo sounder fitted. This will enable you to record the sample position and as well as the depth where you're deploying the BRUVs. These systems will also let you collect some basic mapping data for the study area if none are available. The short-term data management plan describes the data management at the scale of field trips before you get a chance to transfer the data across to your organization's biodiversity data management system. With BRUVing, this data management plan is really important as you very quickly accumulate terabytes of data, hundreds of samples, and loads of pictures and videos that can be used for media purposes. And this all needs to be appropriately stored and named. The plan should include at least 3 main components, which are data collection and documentation. And this will include guidelines for the video management, metadata collection, data curation, and quality control, together with all the supporting paperwork and files. You'll then have your data storage, which includes the SD cards for managing the data while on the boat, and the portable hard drives for capturing all of the data off the SD cards and metadata sheets. Ideally, you should have a standard data storage system on each hard drive to keep all the data neat and discoverable. And then with the hard drives, you must always make sure that you have a second set of backups. Using camera settings suggested in this presentation and the standard GoPro battery, about 4 terabytes of storage space is needed for 100 stereo BRUV samples, so you'll need to plan accordingly when packing hard drives. The last component of the requirements is the data transfer. Again, there are 2 stages, moving the videos on the SD cards and the metadata on the data sheets to the hard drives, and then transferring all the field trip data from the hard drives to your organization's data management system when you're back in the office. With all of these steps, it's very important to ensure that you have appropriate quality control procedures in place to ensure that no data are lost during the process. A simple option for your file management system is to have a template folder system that gets transferred to the hard drives at the start of a field trip and contains all the required templates and guidelines. An example is presented here, with the main parent folder being highlighted in the red box and the first level of subfolders listed below. With stereo BRUVs, you'll need folders for your calibration videos and files, and then it's useful to distinguish between your pre- and post-calibration files. You'll need a folder for your metadata that includes the template data sheets, a place to store photos of your completed data sheets, and then your electronic database file. A folder for your samples will be required, and then for each sample you can have 2 folders, one for the left camera and the other for the right camera. And each folder will be named according to the unique sample code that is in the metadata. You can have a folder tree for your data extraction, which will be where you save your outputs from the video analysis software, and this can also include species lists and ID reference libraries. Your environmental data can have its own folder tree, and this will include the benthos analysis, the field of view analysis, which will include estimating the water column and obstruction. You can have folders for your sensor data and any other important information that was collected during the field trip. And then lastly, you can have a folder tree for the files that will be useful for media purposes. Once you've completed your field trip, you'll need a plan to ensure that the data are appropriately stored and in turn published so that they are open and available for others to use in the future. For BRUVs, this will need to include a plan for video storage. And while you can keep all your data on hard drives that were used in the field, if you intend on collecting lots of BRUVs videos, then a suitable network attached storage system or cloud-based storage system will be more user-friendly and reliable. It's strongly recommended that you keep all your BRUVs videos even after you have extracted the biodiversity data, as they can then be used for other purposes. Also, these videos are ideal to train machine learning applications that will hopefully in the future enable automated annotation of BRUV samples. The second component is the biodiversity data management system, And there are some great online free biodiversity data management options, such as Specify 7 and Global Archive. But whatever option you choose, you should aim to ensure that your data adhere to the FAIR principles, so being findable, accessible, interoperable, and reusable, and that you can easily publish the data to global data management facilities such as GBIF and OBIS. And then lastly, and most importantly, you'll need to develop some form of institutional video analysis capacity. For this, you'll need one or more video analysts who know how to identify the required fishes and benthos, know how to use the software and follow protocols, and then the analysts can also assist in training students and running quality control on the students' data. You'll need video and image analysis software and protocols. Event Measure is a great video annotation tool, and importantly, it allows a second person to perform quality control on the work done by others. If this is not available, then any video media player that permits frame-by-frame control of the video frame playback will work. If you are using stereo BRUVs, you'll also need the calibration software. The Benthic images can easily be annotated in Coral Point Count with Excel extensions, which is freely available. Good computers are obviously a prerequisite, and then you'll also need some additional hard drives for the temporary storage of the samples that are being processed. And then you'll need resources to assist with identification and classification of the fishes and benthos. And that brings me to the end of the presentation. Thanks for your attention, and I hope there was some useful content. If you have any questions, feel free to put them into the chat box. Thanks.
Thanks very much, Ant. Ant is going to introduce his poll. So you should be seeing a poll that comes up, and Ant will take you through that. Thank you.
Good morning, everyone. Yeah, thanks for listening in. Sorry for those if I was speaking a little bit too fast. It was pre-recorded, so I couldn't slow down. But what I will do is I'll provide the PowerPoint presentation with detailed notes for each slide into the supporting documents that go along with the workshop. So you can go through it at your own pace. Basically, the objective for the polls is we're trying to collect some background information on who does BRUV's research within the Western Indian Ocean. So this first one is just to get an idea of the work you do, whether or not you do BRUV's work, and then the type of research questions that you address. And then there'll be another poll a little bit later on looking at the standards, the standard BRUV methods. So yeah, please take your time and answer this if you can. Thanks. So for those who are asking questions about not being able to submit the poll, if you answer no, just if you said no for the first question, then we'll ignore your answers for the rest of the questions. So just make some ticks, any ticks on those remaining questions, and then I'll let you submit. We'll then just disregard those other answers. Thanks for bringing that to our attention. Okay, we'll give you guys a little bit more time to finish off. I can see a few more votes coming in. Okay, great. Thanks very much, everyone. So for the most part, most people haven't done BRUVs related research. There is a mixture of quite an even distribution between BRUVs and stereo BRUVs. But yeah, thanks very much for doing the poll. You can scroll through it. A lot of the people have done coral reef related work in the shallow environments. Okay, great. So next we're just going to play that training video. As I mentioned in the talk, it does repeat a bit of the information that was presented in the PowerPoint presentation. So that should give you a bit more background. Thanks a lot.
Working with stereo BRUVs is an intricate process. This informative step-by-step video will demonstrate how to set up, deploy and operate a stereo BRUVs, as well as how to follow post-deployment protocols. Let's start with what a stereo BRUVs actually is. Baited remote underwater stereo video systems, or stereo BRUVs, are minimally invasive sampling tools used to collect data on the diversity, abundance and size of fishes, as well as information on the benthic habitat where the samples were collected. Benthic stereo BRUVs are deployed on the seafloor, while pelagic stereo BRUVs are suspended in the water column and, depending on your equipment specifications, equipment can be used from the intertidal to the deep sea. In this way, stereo BRUVs provide a standardized and non-destructive method to collect data on fishes and the environments where they occur over their full depth distribution and at scales relevant to management. As the name suggests, stereo BRUVs use bait to attract fish into the field of view of 2 video cameras mounted in stereo configuration. To enable size measurements, the position of the cameras on the stereo BRUVs are calibrated to enable stereo photogrammetry. Stereo BRUVs differ from BRUVs in that they have 2 cameras, whereas BRUVs typically only have 1. Consequently, their ability to collect accurate size data for the fishes from the videos is the core feature that distinguishes stereo BRUVs from BRUVs. Next up, the system's design. To reduce the amount of variability in the design of stereo BRUVs and to maximize the scope for data interoperability, there are internationally accepted best practices, which can be found on the Ocean Best Practice System website. These guidelines, together with the supporting information, provide all the required information needed to assemble and conduct stereo BRUVs research. The core components of stereo BRUVs are a frame, 2 cameras in waterproof housings mounted on a rigid base bar at convergent angles to provide overlapping field of view, and a bait container that can be fixed in front of the cameras. Most stereo BRUVs are tethered by rope to surface marker buoys, so the boat can move away while the videos are recording and to allow easy relocation and retrieval. Additional weights can be added to the frame when sampling in deep water or in areas with strong currents. When working in deep water or at night, artificial lighting can be added. Lastly, sensors to measure the water temperature and depth can be attached to the frame to collect important environmental data associated with a sample. To enable accurate length measurements, the 2 cameras of a stereo BRUVs need to be mounted in a fixed position and calibrated to enable stereo photogrammetry. While in use, it is essential that the cameras don't move to maintain the calibration and allow capture of size data. Detailed notes on the system design options and considerations can be found in the training documents. Let's move on to preparing for a field trip. Prior to leaving on a field trip, you will need to assemble and calibrate the stereo BRUVs and pack all the necessary gear. Detailed information is provided in the supporting documents to this video, but the key steps are to ensure that all housings, cameras and lights are in good working order. The base bars need to be correctly assembled to ensure that the cameras stay in calibration and the details required for each stereo BRUVs, like camera numbers and sensor numbers, are recorded in the project metadata. Adequate quantities of ropes and buoys need to be packed based on the planned sampling depths, number of stereo BRUVs and sampling environment. Once the stereo BRUVs base bars have been assembled, they will need to be calibrated to enable length measurements. In addition, at the end of a field trip, a second calibration must be undertaken as a contingency measure in case the cameras have moved out of calibration while in use. The CAL, or Stereo Camera Calibration Software, developed by CGIS, is the most widely used and capable software for stereo camera calibration. Importantly, the calibration results from the CAL software package can be fed into the Event Measure video annotation software to allow length measurements. Alternative options can be found in the Stereo BRUV's best practices on the Ocean Best Practice System website. The calibration protocol is well documented within the CAL user manual that can be accessed via the software interface, so we won't go into too much detail here. Importantly, the calibration protocol consists of 2 stages. The first is the in-water stage, where the camera calibration imagery is collected. Here, the stereo camera pair is placed in the water to record the calibration hardware, normally a cube, as it is moved and rotated across the overlapping camera field of view. The second stage uses this imagery and the supporting files for the cameras and calibration hardware in the CAL software to run the calibration. The output files are then saved with the appropriate unique identifiers to link them to a camera pair and field trip. The in-water stage will require some initial trial and error to determine the optimal distance for the calibration hardware from the stereo cameras and the horizontal distance of the overlapping field of view. In remote areas, it is important to consider during the planning process that finding a pool with sufficiently clean water to run the calibration can be challenging. For a successful expedition, you will need 1 kilogram of bait for each sample you plan to collect. Fresh or frozen fish bait with a high oil content, like sardines, are ideal, but the choice of bait used should consider availability and allow for comparability between different research locations and projects within your area. Depending on your research location, you may need to travel with the required bait, in which case good cool boxes are essential. While in the field and at sea, you will have to change camera batteries and SD cards and perform general maintenance on the cameras and housings. If working on a small boat, this should all be stored in an on-the-boat BRUVs kit, which includes a watertight container to protect the electronics. The quantity of items needed in the kit depends on the equipment being used. A good boat toolkit is needed to perform the required maintenance to the stereo BRUVs while working at sea and on land. The exact items will be specific to the equipment design, and the researchers should provide checklists to ensure that the important items aren't forgotten. At the end of a sea day, you will be required to record all the sample metadata, download the videos, charge batteries, and clean equipment. With all of these to remember, a comprehensive checklist will save you time and prevent errors. Another important step is determining how you are going to collect your data. Stereo BRUVs have specific requirements to ensure that the samples are independent and adequately sample the fish assemblage. Typically, stereo BRUVs are left on the seafloor to record for 60 minutes, as it results in the highest number of species being detected at their maximum abundances. Another important aspect to consider is sample separation. Because of the bait plume and extended deployment time, adjacent stereo BRUVs samples need to be separated by 400 meters to ensure spatial independence. For shorter deployment times, less separation can be considered. Unless research objectives require otherwise, sampling should not take place at crepuscular times due to changes in fish behavior. Researchers are encouraged to follow these standards to maximize scope for data interoperability, but acknowledge that specific research objectives may require the guidelines to be adapted. As for the design of the sampling, this will depend on the project-specific research objectives. However, it needs to ensure valid inferences and interpretations of the data are possible. When conducting spatial comparisons, employing a spatially balanced approach with stratification according to key environmental variables like depth zone and seafloor habitat, for example, is recommended. Alternatively, when surveying large areas, a clustered sampling design may be more efficient. All research should conduct a pilot study to determine the optimal sample size based on power analysis and species accumulation curves. Next up, field logistics. When using small vessels, the protocol can be split between the work required at sea and the work required when back on land. If the work is being done off a ship, then it may be possible to carry out all required activities at the same time. At sea. For the work to be done out at sea, you will need a suitable vessel with space for equipment and the functionality required for the operations. For bigger stereo BRUVs and deeper water, vessels fitted with a swinging davit arm or pot tipper and winch are ideal for deploying and retrieving the equipment. When working shallow or with lightweight BRUVs, the equipment can be deployed or retrieved by hand. Multiple stereo BRUVs can be deployed concurrently to maximize the number of samples collected per day. The number of systems will depend on availability of stereo BRUVs and the size of the research vessel. For example, it is possible to work with 4 to 6 systems off an 8-meter boat, and during a full day of sampling, you can expect to collect 20 to 30 samples. A typical deployment protocol would involve taking the boat to the predetermined GPS position where you intend to deploy the stereo BRUVs. Once in position, the skipper can check the depth and current while the other team members prepare the system for deployment. Pairing the system for deployment involves starting up the cameras and lights, ensuring housings seal properly, and that the lenses are clean and recording all the required metadata. Attaching the appropriate length of rope and buoys based on the sampling depth. Preparing a fresh container of bait and attaching it to the system. Once both cameras are running and the housings are closed, provide a synchronization point, like a chop on the bait arm for example, that can be used to synchronize the video footage during the annotation process. When ready, the stereo BRUVs are typically lowered to the seafloor using a davit arm and winch or by hand. This approach ensures that the system lands gently and causes minimal damage to fragile benthic organisms. If the boat is fitted with an echo sounder, then it's often possible to view the descent of the stereo BRUVs through the water column, and this enables the descent speed to be reduced just prior to landing on the bottom. Upon landing, the skipper takes a waypoint for the sample using the GPS, and then begins moving the boat away from the position while the crew deploy the rope and buoys. Once clear of the rope, the metadata from the GPS waypoint can be recorded, and the vessel can move to the next deployment site. After the stereo BRUVs has been on the seafloor for 60 minutes, it can be recovered. The objective is not to pick up the stereo BRUVs until the vessel is on the GPS waypoint directly above the stereo BRUVs, as trying to recover it while away from the waypoint will result in the stereo BRUVs being dragged over the seafloor. This could result in the system being snagged in reef, damage to equipment, and/or damage to the habitat. Once the stereo BRUVs is back on board, the research team can check the videos to confirm that the sample worked. The SD cards are then removed and placed in a storage container to be downloaded later. If necessary, light and camera batteries must be changed and new SD cards inserted into the cameras. The researchers then repeat the setting up process and record the relevant metadata for the next sample. Following a day at sea, the research team will need to carry out equipment maintenance and data management. All batteries used during the day will need to be charged and the boat kits repacked when ready. The stereo BRUVs should be rinsed with fresh water. The housing O-rings and O-ring seals should be cleaned and fresh silicone gel applied. Camera and housing lenses should be cleaned. Data should be downloaded off the sensors, such as temperature or depth, correctly named, and transferred to the project data management system. The metadata for the samples collected will have to be transferred to the electronic database, and all of the videos will need to be downloaded from the SD cards into the project data management system. The videos must be named with a unique sample ID listed in the metadata. Once this is complete, a second person should review the files and folders to confirm that everything has been done correctly. Field research typically requires multiple days of sample collection, and the long days can quickly result in fatigue. Having quality control protocols in place will help to ensure that no data and time are lost. Following the successful completion of a research trip, all data will need to be transferred to your organization's data management system. Field trip reports should be compiled, and all equipment will need to be dismantled and thoroughly cleaned. Following this, the biodiversity information from the videos will need to be recorded. This final step will be covered in detail during the training course.
Wonderful. Thank you so much, Anne, for that very informative video and presentation. We've got a number of questions here for you. The first one is about operating standards. Do you have a standard operating environmental condition? For example, are there cutoff points for swells greater than 2 meters or wind less than 10 knots, as an example?
Yeah, so we do have cutoffs and thresholds. We play it by ear quite a bit as well. So, for example, if the morning starts out fine and the wind picks up to 15 knots later, then we'll probably stay out at sea. But we would use a 10, like if it looks like it's going to be blowing 10 knots all day, we probably wouldn't go, especially if the swell is up as well. So yeah, the suggestions there are basically what we would stick to. So 2 to 2.5 and 10 knots. If you've got a 2.5 meter sea and 10 knots blowing all day, then it'll be really horrible. But if you've got a 1 or half a meter sea with a 15 knot wind, then you could probably stay out at sea as well. So it's a bit of a mix and match. So you look at the combination of conditions, and then at the same time you'd include the water current, the sampling depth, the direction of the wind relative to the water current. So ideally you don't want the wind coming at 90 degrees to the current, because then it'll be very hard to position the boat appropriately over the BRUV. So yeah.
Great, thank you. The next question is about the blue and the red lights. Thank you for a wonderful and insightful presentation. Sorry if I missed this. Why do blue and red light are more preferred in the process?
So red light is meant to cause the least amount of disturbance to fishes, especially in the deeper, darker environments or at night. So if you're wanting to observe natural kind of behaviors or not have the lights artificially influencing your data, then the red light would probably be the better one. The problem with the red light is that it dissipates or attenuates very quickly through water. So you don't see a big area. And it's also obviously quite hard to identify the different species of fish because we're used to seeing them under our normal light conditions. So there's pros and cons to red. Blue is the opposite to red. It penetrates the furthest in water. So it lets you see a really big area. But at the same time, it's also quite difficult to identify, especially the small fishes. We actually mostly use white lights now, just because it makes identification of the fish easier. And that's ultimately what you're trying to do. So you're wanting to, like the big fish are always quite straightforward to identify, but the small fish are the ones that are challenging. But if you're investigating ecological type questions, you want to be able to see what those small species are because they play an important role in structuring the ecosystems or defining the ecosystems. So yeah, we use white lights now mostly.
Great, thanks, Ant. We've got a question from my colleague in Gardenroute, Clement. Good morning. You mentioned that you can use CPCE to record benthic invertebrates. How do you calculate area covered using BRUVs or stereo BRUVs? So
we don't. We don't try and standardize it to a density type measure. It's literally just we classify the habitat in a relative type of fashion. So it's relative to the other BRUVs. We're not comparing it to, you're getting it down to per meter squared to then be able to compare it to other methods. And it's only really to support, well, it can be for both, but so it can be used to define the habitats, but it's mostly to support to help explain the patterns in the fish data that we're seeing. Because you get that picture of the habitat, there's no real point in ignoring it when you're interpreting the data. So analyzing it and deciding what the reef profile looks like or deciding what the dominant biota are and can really help interpret the patterns in the fish assemblage.
Great, thank you. We have another question here. Does the stereo BRUV system record the GIS coordinates automatically, or is this done manually before starting the session?
Yeah, so I guess you could use the GoPros, allow you to record position, but we use the boat's GPS echo sounder to record the position. So basically, as you're lowering the BRUV into the water, as you feel it hit the seafloor, you take a waypoint on the boat's echo sounder, and then that gives you the time, the depths, and the GPS position.
Great, thanks, Ant. Then we have another question here. I would like to mention, as per the presentation, the team seems well equipped. Would this be a critic of the quality of the data if this is the standard?
So if I think I understand the question, we are lucky to have quite a bit of equipment, but you don't have to. So people make BRUVs out of, you can make a BRUV out of anything, and you can use any resources you've got, basically. So as long as you're adhering to the standards that have been put forward for BRUVing, then your data will be comparable. It doesn't have to be, it can be quite simple, the work. So as long as you get a system that works, that provides the data, provides comparable data, if it fits within your budget and the data is comparable, then it's great.
Thanks, Ant. We have another question here for you. Thank you for the great presentation. Apart from MaxN, are there any other instances used to identify fish, especially rare species of fish?
So you basically review the entire video, and you identify every single fish in the video that you can. So you do detect the rare species of fish, and MaxN would still give you the abundance of it. So it would still work with the rare fish. Mean count is another method for getting abundance data out of BRUVs, and that basically, instead of watching the whole video and finding one frame, you say you're going to look at 100 points or 50 points or whatever in the video, get the abundance of each species, and then average it out. And that provides a slightly different metric, and there's pros and cons to both MaxN and mean count. The one negative aspect of mean count is that you only view a portion of the video. You don't watch the entire thing, so you might miss the rare species. So for rare species, MaxN is actually quite good.
Great, thanks. Then there's another question here. What is your comment or recap on mapping the benthic information versus area with absence of information, with lack of mapping?
So I'm not entirely sure I follow the question.
Perhaps, Rosabella, you can provide a little bit more clarity, and we can try and answer that. We're running out of time a little bit. There is another question here. Rosabella, try and perhaps clarify what you'd like Ant to address. In the meantime, there's another question here. What is the maximum depth BRUVs can be deployed?
So that's, people do BRUVs related research down to thousands of meters, but ultimately it's your equipment that will set the depth limit. So depending on the depth rating of your underwater housings, that'll determine your BRUV limit. So if you have specifically made housings, though, you can go as deep as you want, and you can then start using lander-based systems for the deep sea. Yeah, so it's up to you and your resources.
Great, thanks. Just while we've run out of time now for this session, Rosabella, please try and clarify your question, and we'll answer it in the typed version. In the meantime, here is another poll that we'd like you to please fill in. And once we've finished with this poll, we'll move on to the next presentation from Sisanda Mayakiso. So please just fill in that poll, and then I'll introduce the next speaker. All right, so for our next presenter on also talking about baited remote underwater video systems is my colleague Sasanda Mayakiso. Sasanda is a junior marine scientist based at the Cape Research Centre in South African National Parks. She obtained a master's in ichthyology from Rhodes University at Grahamstown in the Eastern Cape, and she has experience in the biogeography and population genetics of tropical and subtropical marine fish and reef-associated taxa. So here we go with Sasanda. Take it away.
Good morning, everyone. My name is Sasanda Mayekiso. I'll be presenting a seminar that is entitled Monitoring of Fish Communities at West Coast National Park Using Baited Remote Underwater Video Systems. This sampling technique is relatively low cost, non-extractive, and have a minimal negative impact, making it an ideal monitoring tool for marine protected areas. The nature of this technique permits BRUVs to be deployed in a wide range of depth and habitats. BRUVs have been used throughout the world to monitor species composition and abundance in areas of ecological interest and in and around several MPAs. These are some of the studies that have used BRUVs in areas of ecological interest and in different MPAs. MPAs are widely accepted and have increased in South Africa from 0.4% up to 5% for marine biodiversity to be conserved and protecting their habitat and nursery grounds for a variety of fish, and also allowing recovery of exploited species that were depleting across their range as a result of overfishing. For example, the Rhabdosargus globiceps, which is commonly known as the white stump nose, that is listed as vulnerable on the IUCN Red List of Threatened Species. We have the Langapan Lagoon as an MPA that is part of the West Coast National Park. It holds a Ramsar wetland status and supports a marine biodiversity such as the seabirds and the commercial important fish. And the lagoon serves as a nursery area for juvenile fish. There are also anthropogenic pressures on the lagoon, which include pollution, introduction of invasive alien species, and infrastructure development. There's also a history of fishing which resulted in the depletion of species. These have been recognized increasingly. So the Langapan Lagoon as an MPA uses zones to reduce overexploitation and mitigate anthropogenic factors. As you can see with the map that I have in front of you, the Langapan Lagoon is divided into 3 zones. We have Zone C, which is the sanctuary zone that prohibits fishing and all activities. Then we have Zone B, which is the restricted zone that allows low impact of recreational activities. And also there are no power boats that are allowed here. Then we have Zone A, that is a controlled zone where fishing and activities are permitted. Activities such as swimming and kite surfing. It is therefore important that the performance of the MPA is monitored consistently and regularly. This monitoring program is using BRUVs at Langapan Lagoon in the West Coast National Park to determine whether the method was suitable to use in the lagoon. We also have specific objectives, which include documenting diversity and abundance of fish across the 3 MPA zones and investigating seasonal differences. Monitoring is taking place biannually in summer and winter. Deployments were distributed according to a random stratified design in the 3 MPA zones. The distance between the sites was 500 meters to avoid pseudo-replication. We have used 2 different bait types, but this presentation will not focus on the testing of the two different bait types. We have used 1 kilogram of chopped sardine, and we also filled our bait canister with 1 kilogram of a combination of sardine and red bait. Each deployment lasted for an hour to record. Unfortunately, the visibility of the water outside of the MPA was poor on most of the sampling days, so we decided to discontinue. We have managed to sample 120 deployments, as you can see on my map. All videos were analyzed using VLC, and max-N measure was obtained for each species at every site. Max-N is the maximum number of individuals of a species in a frame for the duration of the video, which is 60 minutes. And these are the statistical packs that we have used. We have used per maneuver to determine whether there are differences among communities using zonation and season. And we also used MDS plots to visualize the differences in species composition and display the effect of zonation and season. And we also have calculated SIMPA to identify the species that contributed towards differences on species composition among the zones. Now I'll be showing you our preliminary results. Preliminary analysis of the videos identified 15 species from 11 families. The Sparidae family was common, representing 5 species, such as the Diplodocus capensis, which is known as the blacktail. The most frequently encountered species were confined in summer. As you can see on the table, I have circled it in yellow. And those zones that had a high relative abundance, I have circled them on the table with red, as you can see. To take you through on the zones that had the high abundance, maybe you did not see them properly on the table. We have zone C and B, which had a high abundance of Spodolysoma imaginatum, which is known as stenky. Zone C had a high abundance of Clinus superciliosus, which is known as the clipfish. We know that the clipfish they're quite complex, but we did not identify them to that extent for our BRUV analysis. Zone B had a high abundance of Atherina breviceps, which is known as the Cape silverside. Our summer months had a greater diversity in Zone A, which is followed by Zone C. Coming to our Permanova for community composition, our Permanova had showed the interaction between zonation and season, indicating that the effect of zonation on community composition is determined by season, and pairwise have confirmed summer. Coming to our MDS, for community composition, Our MDS is showing some distinction on community composition. Our simple model is showing us the species that contributed towards differences on species composition among the zones in summer. As you can see in our table, those that I have circled in red, that is the Atherina breviceps and the Spordylysoma imaginatum that are prevalent in zone B and C. And those that I have circled in yellow, that is the Clinus superciliosus in zone A and Rhabdosargus globiceps in zone A and B. According to the simple model for winter, as we can see in our table, we are not seeing a lot of fish. And we are also have observed that in our table now that the Spordylysoma imaginatum, it's now in zone, we are seeing it now in zone A. And we are also picking up that the Rhabdosargus globiceps is in zone C. We are also picking up new species that we did not see in summer. With 120 successful BRUV deployments, the BRUVs were not evenly deployed between season, especially for winter samples. This was due to the harder lockdown because of the COVID-19 in 2020. And this year, it was because of the restrictions of the level 4. Although in our monitoring program, we have identified a lower number of species compared to other studies, but we have identified the species that were recorded in the SANET surveys that were done in Saldanha and Langaban Lagoon. And in our videos, we also have recorded the spear-nose skate and the smooth-hound shark, which was not recorded in the SANET surveys. And our videos were also dominated by the sea bream family, as seen in other surveys. Summer months have a greater community composition and diversity. This could be attributed to the high temperature in summer and visibility that increases and attracts a larger abundance of fish. Another possible explanation could be that most of the fish, they use the lagoon as a nursery area, and the summer months coincides with the peak spawning. For example, the Rhabdosargus globiceps spawns during summer. Another possible explanation for not picking up most of the fish during the winter season, this could be that the fish might have migrated to the bay, spending June to August, that is in winter, in Saldanha, and those that exhibit residency remain in the lagoon, in the zones that are suitable for them. The preliminary results demonstrate that BRUVs are viable method for monitoring fish, especially those of species of special concern. And our recommendations are to continue deploying BRUVs as a long-term monitoring tool and to expand it to the islands of the MPA. And we would like to acknowledge the following partners and the people that have helped me a lot for this monitoring program. And we would like to thank you for your attention.
Thank you very much, Sasanda. I know that it's been a lot of work getting this monitoring program running. I thank you very much for an informative talk and for presenting some of the preliminary results. My first question to you is, you've done BRUV sampling in the marine environment in Table Mountain National Park, MPA, as well as the lagoon estuarine environment of Langebaan. What are the key differences for you in working in these two different habitats?
Good morning, Alison. Thank you for that question. Working with the BRUVs at Table Mountain National Park, when we were deploying the BRUVs, they would land upright. But when we were deploying the BRUVs in the lagoon, I think the wind was too strong and also the current. So most of the time when we were deploying the BRUVs in Langebaan Lagoon, they would mostly capsize. So I had to come up with a solution on how I can be able to secure that, as Ant has mentioned. So we decided that to use that floating a buoy, so that we can be able, so that our BRUVs can land nicely and not capsize on the lagoon.
Yes, yeah, those tidal movements in the lagoon are very strong, and they definitely cause some equipment issues.
Yeah.
I have another question for you. What was some of your kind of challenge for you in working with BRUVs? We've seen with Ant's presentation, there's a lot of work involved in terms of prepping your equipment, working with electronics on the boat, getting the bait sorted, and you usually have a relatively small team, and we work on very, very small boats, much smaller than 8 meters, Ant. And so what are some of your challenges that you've experienced in deploying BRUVs in the environment, and maybe some key lessons or advice for people wanting to use BRUVs?
Okay, on my side, I have a genetics background. So now I had to shift to ecology. I had to do a lot of reading and also how to set up the equipment as well and how to design the frames. But I also had to do some consulting on, I have to do some consulting, going to people that have worked with BRUVs so that they can be able to see of whether if I'm on the right track with my designing of my still and the GoPro cameras and all those things that I have to use, and also what do you call it? And also reading the manuals that I have actually downloaded and looking at the literature. So the literature has helped me a lot. But according for this, what do you call it? For this workshop that I'm in right now, I'm learning a lot, and I can see with Ant, they're quite advanced. They have a lot of resources and capacity, whereas in my team we are only 2, but now we are 3 with our intern.
Great, Sasanda. We've got a question here for you. Lovely presentation, Sasanda. Thank you for sharing. I'm just curious to know, in terms of the long-term monitoring program within the lagoon, would you and the team consider BRUV sampling in autumn and spring as well? And if not, why?
In autumn and in spring. Hey. We decided to do it the way that other BRUV surveys, they were doing it. They were mostly doing it in summer and in winter biannually. So with that option of including autumn and spring, maybe I'll think about it and then see on literature on the Langalpan Lagoon what we can see and what we can observe during that period before I can include it in.
Great, thank you, Sasanda. I think also just to perhaps talk to that a little bit. We monitor 5 marine protected areas using BRUVs, and we're only a team of 3 people. And so to get to all the marine protected areas, one needs to try and find the right seasons and enough days to be able to do that. So one of the limiting factors is the amount of capacity and staff available to go out into the field. Thank you very much for that question. We've got another one here for you, Sasanda. How long does it take to watch and analyze your videos? Also, do you find it better to watch one video reader than another, or have 2 video readers on at one time?
Okay, when I first started analyzing my videos, I was caught, I did co-learning at first. I was taught by someone at UCT, Lauren DeForth, who has helped me a lot on how to analyze the videos. So I was quite slow at first. And then now, at least I am quite faster than before in analyzing the videos and also identifying some of the species.
And can you give us an indication of how many hours it took you in the beginning versus now?
Yeah, it would take me longer at first, and I would not be sure with some of the species, so I had to go and consult. But I would use the relevant books that I'll be using. So I was used to SciEd, where there's those books. That way we can be able to identify these species. So here we have less books in our organization. So, but with the help of the people and for me with myself being able to identify and also using that knowledge that I had of fish, I was able to identify. So now it takes me about, if I'm looking at the video for an hour video, it takes me now an hour, but it used to take me about 2 to 3 hours at first. But we learn as time goes by. Even with the stats now, I'm learning with the softwares. So it was a good thing that I got that they were sharing those blogs that I can be able to go and learn on how to use the stats. So as time goes by, I'll improve.
Absolutely, Sasanda. And I think this is what this is all about, this workshop, sharing knowledge and learning new things and helping each other to advance the science and to gather the knowledge that we need. So yeah, very well done to you on how far you have come. We've got another question here for you. Very nice presentation. How much does a BRUV system cost? And how much does it cost to work in the lagoon?
Oh, can you help me with that, Alison, as well? Can you please chip in? I know with the cameras, the GoPros were 5, is it 4? How much did you spend?
A GoPro system with the camera and the rope and the floats and the memory cards and the batteries cost about, in total, about 10,000 Rand per BRUV system. We, in our study, we use 5 different systems. And then in terms of the operating costs, once you've got the equipment, the operating costs are the cost of a boat. We're lucky in Sandparks that we have got several boats that we can use. So we don't have to pay for boat charters. And then it's the cost of the fuel, so the petrol that you use, and then of course staff costs come into that. But basically, once you've got the equipment, then the operating costs are relatively low. Excellent. So thank you so much, Sasander. Thank you, Ant, as well. We are running ahead of time a little bit. Are there any more polls that we want to show before we break for tea? I don't think there's another poll before tea. So we're going to break for tea now. We'll start again at 11 o'clock. But for those of you that are interested in watching the training video in French, that's going to be playing throughout the presentation. So I do see there is another poll that has popped up on your screens. So yeah, please take a moment to fill in that poll and submit that, and then enjoy your tea, and we'll see you back at 11 o'clock.
Travailler avec des stéréo-BRUVs est un processus complexe. Cette vidéo informative, étape par étape, démontre comment installer, déployer et faire fonctionner un stéréo-BRUVs, ainsi que comment suivre les procédures de post-déploiement. Commençons par expliquer ce qu'est un stéréo-BRUVs. Les BRUVs, Baited Remote Underwater Stereo Video, égale à système stéréo-vidéo rotative appâté actionné à distance ou stéréo-BRUVs sont des instruments d'échantillonnage peu invasifs utilisés pour recueillir des données sur la diversité, l'abondance et la taille des poissons, ainsi que des informations sur les habitats benthiques où les échantillons ont été recueillis. Les BRUVs benthiques sont déployés sur le sol marin alors que les stéréo-BRUVs pélagiques sont en suspension dans la colonne d'eau et selon les spécifications de votre équipement, ce dernier peut être utilisé de la zone interdidale jusqu'en haute mer. De cette façon, les BRUVs fournissent une méthode standardisée et non destructive pour recueillir des données sur les poissons et sur les environnements où ils se trouvent, ainsi que sur leur répartition en pleine profondeur et à des échelles pertinentes pour la gestion. Comme leur nom l'indique, les BRUVs se servent d'appât pour attirer les poissons dans le champ de vision de 2 caméras vidéo montées en configuration stéréo afin de pouvoir prendre les mesures détaillées. Les positions des caméras sur le stéréo-BRUVs sont calibrées pour activer la stéréophotogrammétrie. Les stéréo-BRUVs diffèrent des BRUVs par le fait qu'ils disposent de 2 caméras, tandis que les BRUVs n'en ont habituellement qu'une seule. Par conséquent, leur capacité à recueillir des données précises sur la taille des poissons à partir des vidéos est la caractéristique principale de distinction entre ces 2 systèmes. Prochaine étape, la conception du système. Afin de réduire la variabilité dans la conception des stéréo-BRUVs et d'étendre au maximum le champ d'application pour l'interopérabilité des données, il existe de bonnes pratiques reconnues à l'échelle internationale que l'on peut trouver sur le site web du guide de bonnes pratiques dans l'océan. Ces directives ainsi que la documentation à l'appui fournissent l'ensemble des informations requises et nécessaires pour préparer et effectuer une recherche à l'aide des stéréo-BRUVs. Les composants principaux des stéréo-BRUVs sont une armature, 2 caméras dans des boîtiers étanches montées sur une barre de support rigide à angle convergent afin de fournir un champ de vision se chevauchant et un récipient d'appât pouvant être fixé devant les caméras. La plupart des stéréo-BRUVs sont fixés par des cordes au bouillet de marquage de surface pour que le bateau puisse s'éloigner pendant que les vidéos sont enregistrées et pour faciliter les déplacements et la récupération. Des poids supplémentaires peuvent être ajoutés à l'armature lors d'échantillonnage en eau profonde ou dans des zones de fort courant, lors d'un travail en eau profonde ou pendant la nuit, un éclairage artificiel peut être ajouté. Enfin, des capteurs pour mesurer la température et la profondeur de l'eau peuvent être attachés à l'armature afin de recueillir des données environnementales importantes liées à l'échantillon. Pour pouvoir prendre des mesures de longueur précises, il est nécessaire de monter les 2 caméras dans une position fixe et de les calibrer afin de mettre en œuvre la stéréophotogrammétrie. Pendant leur utilisation, il est impératif que les caméras restent mobiles afin de maintenir le calibrage et permettre la capture de données de dimension. Des notes détaillées sur les options et les considérations relatives à la conception du système se trouvent dans les documents de formation. Parlons maintenant de la préparation de la mission. Avant de partir en mission, vous devrez rassembler et calibrer les stéréo-BRUVs et préparer tout l'équipement nécessaire à emporter. De plus amples informations sont fournies dans les documents en appui de cette vidéo, mais les étapes clés consistent à s'assurer que tous les boîtiers, les caméras et les lampes sont en bon état de fonctionnement. Les barres de support doivent être correctement assemblées afin de s'assurer que les caméras restent bien calibrées et que les informations nécessaires pour chaque stéréo-BRUVs, telles que les numéros des caméras et des capteurs, soient enregistrées dans les métadonnées du projet. La bonne quantité de cordage et de bouillie doit être préparée en fonction de la profondeur des échantillonnages prévus, du numéro des stéréo-BRUVs et de l'environnement d'échantillonnage. Une fois les bases de support des stéréo-BRUVs sont assemblées, il faut les calibrer afin de pouvoir prendre des mesures de longueur. Par ailleurs, à la fin d'une mission, un second calibrage doit être réalisé à titre exceptionnel au cas où les caméras se soient déréglées pendant leur utilisation. Le CAL, ou logiciel de calibrage stéréo, développé par CGIS, est le logiciel le plus largement utilisé et le plus performant pour le calibrage de caméras stéréo. Qui plus est, les résultats de calibrage du logiciel CAL peuvent être rentrés dans le logiciel d'annotation Video Event Measure afin de pouvoir prendre des mesures de longueur. Vous pourrez trouver d'autres options sur le site web du guide de bonnes pratiques dans l'océan. Le protocole de calibrage est bien documenté dans le manuel d'utilisation du logiciel CAL, accessible via l'interface du logiciel. Nous n'entrerons donc pas trop dans les détails ici. Ce qui importe, c'est que le protocole de calibrage comporte 2 étapes. La première est l'étape en milieu aquatique pendant laquelle les images de calibrage de la caméra sont recueillies. Ici, les 2 caméras stéréo sont placées dans l'eau pour enregistrer le matériel de calibrage. En principe, un cube, au fur et à mesure de son déplacement et de sa rotation sur le champ de vision de la caméra qui se chevauche. La deuxième étape utilise ces images ainsi que les fichiers supplémentaires pour les caméras et le calibrage matériel dans le logiciel CAL pour lancer le calibrage. Les fichiers de sortie sont ensuite sauvegardés avec les identifiants uniques appropriés afin de les associer aux 2 caméras et à la mission. L'étape en milieu aquatique nécessitera plusieurs essais afin de déterminer la distance optimale pour le calibrage matériel depuis les caméras stéréo et la distance horizontale des champs de vision qui se chevauchent. Dans les zones reculées, il est important, durant le processus de planification, de prendre en considération que trouver un bassin avec suffisamment d'eau propre peut s'avérer difficile. Pour une mission réussie, vous aurez besoin de 1 kg d'appât pour chaque échantillon que vous avez l'intention de prélever. Des appâts de poissons frais ou congelés à haute teneur en huile sont idéales, mais le choix de l'appât utilisé devrait tenir compte des disponibilités et permettre d'établir des comparaisons entre les différents sites de recherche et les projets dans votre région. Selon votre lieu de recherche, vous pourriez avoir besoin de voyager avec l'appât nécessaire, auquel cas de bons glaciaires sont indispensables. Lorsque vous serez sur le terrain et en mer, vous devrez changer les batteries de la caméra ainsi que les cartes mémoire SD et effectuer un entretien général des caméras et des boîtiers. Si vous travaillez sur un petit bateau, tout cela doit être stocké sur le bateau dans un kit BRUV, comprenant un contenant étanche pour protéger les composants électroniques. Le nombre d'articles nécessaires dans le kit varie selon le type d'équipement utilisé. Un bon kit d'outils est essentiel pour effectuer les travaux d'entretien nécessaires du stéréo BRUV lors de travail en mer et sur terre. Le nombre précis des articles sera propre à la conception de l'équipement et les chercheurs doivent fournir des listes de vérification pour s'assurer que des articles importants ne soient pas oubliés. À la fin d'une journée en mer, il vous faudra enregistrer toutes les métadonnées, télécharger les vidéos, recharger les batteries et nettoyer l'équipement. Pour ne rien oublier, une liste de vérification complète vous permettra de gagner du temps et d'éviter les erreurs. Il est également important de déterminer comment vous allez recueillir vos données. Les stéréo BRUV ont des exigences particulières pour s'assurer que les échantillons sont indépendants et échantillonnent correctement les groupements de poissons. Le plus souvent, les stéréo BRUV sont laissés sur le fond marin pour un enregistrement de 60 minutes, vu que cela donne lieu à la détection du plus grand nombre d'espèces à leur abondance maximale. Un autre élément important à prendre en compte est la séparation d'échantillons. En raison de l'appât, mouche de pêche et de la durée de déploiement prolongée, des échantillons stéréo BRUV adjacents doivent être espacés de 400 mètres pour assurer une indépendance spatiale. Pour des déploiements d'une durée inférieure, un espacement moindre peut être envisagé. Sauf si les objectifs de recherche l'exigent, l'échantillonnage ne doit pas avoir lieu au crépuscule en raison de changements de comportement des poissons. Les chercheurs sont encouragés à respecter ces normes afin de maximiser les possibilités d'interopérabilité, mais reconnaissent que des objectifs de recherche précis peuvent exiger que les lignes directrices soient adaptées. Quant à la conception de l'échantillonnage, elle dépendra des objectifs spécifiques du projet de recherche. Cette conception doit cependant permettre les inférences et les interprétations de données. Lors de comparaisons spatiales, il est conseillé d'adopter une approche spatiale équilibrée avec stratification conformément aux variables écologiques, telles que, par exemple, la profondeur de la zone et l'habitat du fond marin. Alternativement, lors de l'arpentage de vastes zones, un plan d'échantillonnage groupé serait peut-être plus efficace. Toute recherche doit commencer par la réalisation d'une étude pilote afin de déterminer la taille optimale de l'échantillon, reposant sur l'analyse de puissance et les courbes d'accumulation d'espèces. Vient ensuite la logistique de terrain. Lorsqu'on utilise de petits bateaux, le protocole peut être divisé entre les travaux requis en mer et les travaux requis au retour à terre. Si les travaux sont réalisés à bord d'un bateau, alors il peut être possible d'effectuer toutes les activités requises en même temps. En mer. Pour les travaux à effectuer en mer, vous aurez besoin d'un bateau adapté avec assez d'espace pour l'équipement et ayant la fonctionnalité requise pour effectuer les opérations. Pour les plus grandes stéréo BRUV et dans des eaux plus profondes, des navires équipés de bras de bossoir pivotants ou d'un basculeur de conteneurs et d'un treuil conviennent parfaitement au déploiement et à la récupération de l'équipement. Lors de travaux dans des eaux peu profondes ou à l'aide de BRUV légers, l'équipement peut être déployé ou récupéré manuellement. Il est possible de déployer plusieurs stéréo BRUV simultanément afin de maximiser le nombre d'échantillons recueillis par jour. Le nombre de systèmes dépendra de la disponibilité des stéréo BRUV et de la taille du bateau de recherche. Il est possible, par exemple, de travailler avec 4 à 6 systèmes sur un bateau de 8 mètres et au cours d'une journée complète d'échantillonnage, vous pouvez vous attendre à recueillir de 20 à 30 échantillons. Un protocole typique de déploiement suppose amener le bateau à la position GPS prédéterminée où vous avez l'intention de déployer la stéréo BRUV. Une fois en position, le skipper peut vérifier la profondeur et le courant pendant que les autres membres de l'équipage préparent le système au déploiement. Préparer le système au déploiement implique de démarrer les caméras et d'allumer les lumières, en s'assurant que les boîtiers ferment bien, que les objectifs soient propres et que l'enregistrement des métadonnées requises s'effectue correctement. Attacher la bonne longueur de cordage et le bouiller en fonction de profondeur d'échantillonnage. Préparer une nouvelle boîte d'appât et l'attacher au système. Dès que les deux caméras sont en marche et que les boîtiers sont fermés, donnez un point de synchronisation comme un repère sur le bras d'appât par exemple, pouvant être utilisé pour synchroniser les images vidéo pendant le processus d'annotation. Dès qu'ils sont prêts, les stéréo BRUV sont généralement descendus sur le fond marin à l'aide d'un bras de boussoir et d'un treuil ou bien manuellement. Cette méthode permet au système d'atterrir doucement et ne cause que des dommages minimes aux organismes benthiques fragiles. Si le bateau est équipé d'un échosondeur, alors il est souvent possible de voir la descente du stéréo BRUV dans la colonne d'eau et cela permet de réduire la vitesse de descente juste avant l'atterrissage au fond. Au moment de l'atterrissage, le skipper prend un point de repère pour l'échantillon à l'aide du GPS et commence à éloigner le bateau de la position pendant que l'équipage déploie les cordes et les bouliers. Une fois les cordes dégagées, les métadonnées du point de repère du GPS peuvent être enregistrées et le bateau peut se déplacer jusqu'au prochain site de déploiement. Après 60 minutes passées sur le fond marin, le stéréo BRUV peut être récupéré. Le but est de ne pas récupérer le stéréo BRUV jusqu'à ce que le bateau se trouve sur le point de repère du GPS directement au-dessus du stéréo BRUV, car tenter de le récupérer quand il est loin du point de repère aura pour conséquence que le stéréo BRUV sera traîné sur le sol marin. Le système pourrait alors rester coincé dans le récif et l'équipement et ou l'habitat est endommagé. Dès que le stéréo BRUV est à nouveau à bord, l'équipe de recherche peut visionner les vidéos pour s'assurer que l'échantillonnage a bien fonctionné. Les cartes mémoire SD sont ensuite retirées et rangées dans une boîte pour être téléchargées ultérieurement. Si nécessaire, les lampes et les batteries des caméras doivent être changées et de nouvelles cartes de mémoire SD insérées dans les caméras. Les chercheurs répètent ensuite le processus de configuration et enregistrent les métadonnées pertinentes pour le prochain échantillonnage. Après une journée en mer, l'équipe de recherche devra effectuer l'entretien de l'équipement et la gestion de données. Toutes les batteries utilisées pendant la journée devront être rechargées et l'équipe de bateau remballée une fois prêt. Le stéréo BRUV doit être rincé à l'eau douce. Les agneaux et les joints toriques doivent être nettoyés et du gel de silicone appliqué. Les objectifs et les boîtiers des caméras doivent être nettoyés. Les données doivent être téléchargées des capteurs, tels que la température ou la profondeur être identifiées correctement et transférées dans le système de gestion des données du projet. Les métadonnées pour les échantillons déjà recueillis devront être transférées dans la base de données électroniques et l'ensemble des vidéos devra être téléchargé des cartes mémoire SD dans le système de gestion des données du projet. Les vidéos doivent être identifiées avec les identifiants uniques et d'échantillons répertoriés dans les métadonnées. Une fois terminé, une deuxième personne devra vérifier les fichiers et les dossiers afin de confirmer que tout a été fait correctement. Les travaux de recherche sur le terrain nécessitent généralement plusieurs jours d'échantillonnage et les longues journées peuvent rapidement entraîner de la fatigue. La mise en place de protocoles de contrôle de qualité permettra d'éviter la perte de données et de temps. Après le bon déroulement de la mission scientifique, toutes les données devront être transférées dans le système de gestion des données de votre organisme. Des rapports de mission devront être rédigés et tout l'équipement devra être démonté et nettoyé soigneusement. Ensuite, les données sur la biodiversité à partir des vidéos devront être enregistrées. Cette dernière étape sera traitée en détail pendant la formation.
Welcome back, everybody. I hope that you enjoyed your tea. We're going to be continuing with session 5 now. Please remember to choose your audio channel, English or French, and use the Q&A function to ask questions to the presenter. Our third speaker in this session is Roxy Juby. Roxy is a senior video analyst at SIA who assists with the processing, training, and management of students and analysts, quality control and data management of baited remote underwater stereo video systems for data collected around South Africa and within the Western Indian Ocean. Please take it away, Roxanne.
morning, everyone. My name is Roxanne Juby, and I work with Dr. Anthony Bernard from SIAB, the South African Institute for Aquatic Biodiversity. Dr. Anthony Bernard manages the Marine Remote Imagery platform, and I assist the platform with video processing, habitat descriptions, quality control, as well as training the analysts and data management. So for today's talk, it's going to be a 30-minute talk, and I'm a bit pressed for time. So with the video processing, it's going to be quite a quick run through. Habitat descriptions we'll spend a bit more time there, and then quality assurance and quality control will also run through quite quickly. So for the video processing of stereo BRUV's footage, I'm just going to quickly introduce you into the data that we're going to be extracting from the videos, the software used to do this, as well as the standard operating procedures used by the MARA platform. Okay, so if we're looking at the video processing, we aim to extract species lists, species abundance data, and fish length data from each video sample. So your species lists are extracted by identifying all individuals that are seen in a 16-minute video from the time that the system settles on the sea floor. The species abundance is extracted in the form of max N. This is the maximum number of individuals per species seen in a single frame. So this is a conservative estimate of relative abundance, and it just ensures that you are not counting the same individual twice in a given video. The fish length data, we extract the fork length, so that's from snout to caudal fork. This is, however, only available from stereo BRUV's data, and that is your systems that have 2 video cameras, and it's also only possible to extract using CGIS software. Okay, so the CGIS software called Event Measure is something that we use at the platform. It is rather efficient when trying to extract species lists, species abundance data, as well as length data. In addition to being able to extract fish length data, you are able to get visibility estimates for each sample, and you can calculate the distance from the system to a fish. So that opens doors for your research questions. You could look into behavior of species and how close they approach the video camera. With Event Measure, you are able to upload a standardized user-defined species code file. And this just includes all of the species that you should see in the region, and it just limits any data entry errors, spelling errors, etc. All data exported in Event Measure comes out as a single Excel file, one for your max N data and then one for your length data. The alternative is VLC Media Player, and you can create very similar Excel files from this. However, it is a lot less efficient, obviously, as you are doing all the manual recording. There's also obviously a higher chance of data entry errors since it is manually recorded and there are no standardized code files used. And also you aren't able to extract any 3D measurements. So if I look at the standard operating procedures that we use, they are obviously a lot more comprehensive than this, but the basics is that we analyze each video for a 60-minute analysis period from the time the system settles on the sea floor. We only identify individuals and find a max N value for species using the left video. Both videos are only used to measure individuals at their max N frame, as well as to estimate visibility, which is also a measurement. The way we extract visibility is to measure the distance from the furthest most identifiable fish in the 1 hour video period. Okay, so this is just an example of how we set up Event Measure. This is its home page, and basically you are able to load the left video as well as the right video, and then we find a synchronizing point in both the videos, and we are able to lock the videos together in Event Measure so that the videos work together. This is an example of a file created in Event Measure. So for each sample that you analyze, you will create an EMOB, and you can see that all of the different species have already been identified along with their genus and family names. and their max N values. Okay, so if we play a movie, this is just an example that we've seen a new species. So you will watch the species, you will close player and update position, and then you will be able to add a point underneath the fish. Using that species code file that I've already discussed, it comes out as a drop-down menu, so all the species are already there. You just have to select the appropriate species that you want, along with its genus and family name, and then the number of individuals, the stage, as well as the activity, depending on your research question. And you can press OK. So as you can see now, the point is made on the video directly, and the time and the frame is all recorded, and this is exported with the data as well. Okay, so now this is the max N frame for this individual. Say, for example, we didn't see the same species again in the video. So now we want to find a point in the video around this max N frame where the individual is at a very good angle for us to take the most accurate length measurement. So what we need is a nice straight fish with a nice view of its snout and caudal fin in both the left and right videos. We just click on the snout and we click on the caudal fork, and we are able to get all the species information up, as well as the length in millimeters. Okay, so now we're going to be moving on to benthic descriptions of habitat images extracted from stereo BRUV's footage. We have a bit more time to work through this section, so I'll introduce you to the data and why it's important, the approaches and software that we use, and the SOPs that we follow. Okay, so benthic habitats influence the observed reef fish community. And although when we deploy our systems, we do try to target reef, the benthic features of a habitat are always different. And this is important to consider because it can help describe observed fish patterns, it can help reveal fish habitat relationships, or alternatively, the habitat data can simply be used independently in order to define habitats of a location. So when I speak about how a habitat might differ, it might be the different features such as the complexity. Here we have a very high reef profile. On the right, we have a very low profile habitat. We also have very different substrates that dominate the reef, dominate the habitat. So here it's dominated by sand, whereas here it's dominated by rock or reef. The biota that's present is also important to take into consideration, such as its morphology and its type and its class. And then lastly, the field of view. So how much open water there is in comparison to seafloor. Okay, so at MARIP, which is our platform, we do a relatively course level approach, and then we can also do a more detailed describing the benthic habitats approach. So for the course level approach, we do this very quickly while extracting fish abundance data in event measure. And it basically only gives us an example of the relief or substrate that is present. So we wait for the system to settle on the seafloor, and then we decide and classify the sample according to one of 6 standard categories, either 100% sand, sand inundated reef if there is reef present in the sand, reef high versus reef low depending on the profile, and then if there's a combination of reef and sand, we look at the profile as well and come up with patch reef high or patch reef low, and that is it. When we look into the field of view, we use a free software that's available online called Vidana, and we simply load the habitat image into Vidana and color in the seafloor, and the software estimates the percentage of this field of view that is characterized by seafloor versus open water. We can also use this software to come up with a percentage of obstruction. So for example, if there was a big reef feature that was obstructing any view of fish that were swimming behind that feature, we would be able to account for that by finding out the percentage of the field of view that we cannot see. Okay, then I spoke about the more detailed approach, and this is what we're going to go through the SOPs a bit more closely. This basically scores the benthic composition and relief from habitat images. And there are multiple methods and multiple classification schemes followed, and they all produce comparable data. At SciAb, our approach is based on Langlois et al., and it's a common sense and hybrid systematic approach. It uses the Katami classification scheme with slight modifications. And if you are interested, you can find the approach and the scheme all in an open access repository online. Okay, so if I'm speaking about a code file, this is what I'm referring to. We use a standard code file that is based on the Katami classification scheme called a CAB file. This was produced to improve standardization when describing marine benthic habitats in Australia. The reason we use this is because it's also used by Langlois, and they modified it slightly to include additional class levels. So on your right, you have the Katami classification scheme, just illustrated as a tree, and you can see all the different categories. You have some that are broad and some that go into more detail. So this is rather broad and that goes into more detail. At SciAb, our research group worked together to modify the file slightly further to ensure that it represents the habitats that we sample along the southeastern African coastline. So our code file, which looks something like this is basically just all the categories listed along with a unique code. And it includes multiple broad and more detailed categories on substrate, biota, morphology, and type. And then it also includes a level of relief. So 1 being very flat and 5 being very complex. Like I said, these code files are customizable. Okay, so when I said our approach is a hybrid systematic approach, it just means that we follow a system in order to improve standardization across the habitat descriptions. So you basically set up your habitat image so that you have a specified grid overlaid onto the image. You can find all the details of this grid online on the Langlois page that I'll show you a bit later. And basically, just like a book, you work your way from point to point, working from left all the way to right, defining the nearest dominant feature underneath that point or closest to that point, if that makes sense. We will work through it now. So while we follow a system, it's also a bit of it requires a common sense element. So before you analyze the image, we ask that you do view the whole image, notice the relief as well as the dominant versus rare features, the substrates and biota, and come up with what you expect. You know, what is the idea? What is the type of habitat that you expect should be shown by the habitat description process? Then once you have completed the systematic approach where you're defining every single point, use your notes to adjust your systematic outcome if it differs substantially from your common sense expectations. So what we're saying is standardization is important, but accurately describing the habitat is also important. So ensuring that your data is representative of what you are actually seeing. Okay, so at SciAb, our platform uses 2 software to carry out habitat descriptions. The CGIS Transect Measure software, it is very efficient. However, you do require a software key to use it. There is CPCE, which is Coral Point Count. It's freely available. And this is what we'll work through today, just because it's available to everyone. And when these software are used in combination with the SOPs, they produce completely comparable data. Both of these software require habitat images as well as the code file in order to create a single text or Excel file that summarizes the area calculations that you decided on for each image. In the process, every single sample is analyzed and a software file is created called a TMOB file in Transect Measure, and a CPCE file in CPCE. Okay, part of our SOPs is important file management, and I haven't shown you the whole structure of our file management folder system, but for habitat descriptions, it's important to create a single master folder, and within this master folder, create subfolders for each day that you are analyzing, and then you name it according to the date. Within each dated subfolder, you need the files that you need to do the analysis, so your habitat images and your code file. And then you can save all of your files that you created after analyzing those habitat images. So it's just easier when using CPCE because it's a freely available software. It's not as user-friendly as Transect Measure. And when exporting the data, it's just simpler if all the files that you analyzed and used to analyze are all in a single folder every time that you analyze. So this is just an example of how we extract habitat images using VLC Media Player, because this is a free software. I thought I'd show you how we do it. So you just play so that the system is deployed off the boat and moves down onto the sea floor. This can also be done in Event Measure. And you just bring the system down to the sea floor until the sand and everything settles around it, and you make sure that you've got a clear view of the reef with no fish. If you go to the bottom left, you can pause it, and then you can also click the camera icon, which will take a screenshot of the habitat. If you go to Tools and Preferences, you'll be able to find the directory where your sample is saved, and you should be saving this habitat image as the sample code within your dated folder. Okay, so if you open up your CPCE, you'll get your home page, and this is what it looks like. The first thing you want to do is you want to load the images as well as your code file that you need. So basically, you are going to go to Options in the top panel there, and next to Options, just waiting for the mouse, Options, specify code file, and it will take you to your master folder. Inside your master folder is your dated subfolder. And inside there should be saved your text file that is your code file. Click Open. Then you want to load your habitat images. So to do this, you go to File, Multiple Images or File Processing, Process Multiple Images, and you want to locate the drive in which your master folder is saved. You then want to double click on your subfolder, your dated subfolder, and all of the habitat images that are saved in there will be highlighted. Okay, so automatically this window comes up, and this is just to specify the border boundaries of the grid that is going to be overlaid onto your habitat image. What we do is we specify it according to the WIO approach. So all of these numbers are available online. But basically you want to click specify border offset and make sure that the X offset is 150 and the Y offset is 100. Okay, immediately this header information will come up along with the grid, and on the right hand side is where you will enter all of your habitat descriptions. So you will need to fill this window out for every single sample. At our platform, a lot of these fields are already entered in our metadata sheet, so we don't think it's necessary to complete all of them, but only our sample code. So at the top, we've got the station cell. This is where we place our sample code. And if your habitat image is saved as your sample code, then you can just use the top name as a reference. So we just type it in. And then we also want to just include our analysis date, just to know when the analysis was done, but also this helps with locating the files, and then the analyst name. Okay, then you're going to press Save Header Data, and it's going to ask you, or show you that it's been saved, and then you want to close. Okay, lastly, to set up your CPCE, you just want to make sure that the points are overlaid. So at the top, you click on Point Overlay, specify or apply overlay points. And again, you just want to make sure that it's a uniform grid, and the number of rows is equal to 5 and the number of columns is equal to 7. And again, these numbers are available in the WIO quick guide, which is available online, and click Overlay Points. Okay, so you're basically ready to start analyzing now, and you can see that all the points are present. And like I said, you analyze from the top left and work your way down to the last 35th point in the same direction as you would read a book. Okay, if you want to zoom in, you just left click. If you want to zoom out, you just right click. And there's also image enhancement tools available at image tools, image enhancement, and it will give you the instructions on how to do this. But basically you just draw yourself a little rectangle and it will enable you to change the brightness, sharpness, contrast, and color balance of the image. And you can reset this if you need to, and press close. Okay, so we can basically start analyzing. You do want your code file handy when you are analyzing, and you're going to start at the top left. Of course, there is the, and then you will fill out, sorry, for every single point, you will fill out the ID code next to the relevant point. And then in the notes section, you will fill out the relief level. Okay, so in this point A, you can obviously see the housing of the camera, but we know that it is open water that is nearest, or open water is the dominant feature nearest to this point. So we want to go to our code file, find open water's code, and there it is. The code is NBOW. So that is what we need to remember in order to type it into the ID cell next to point A. So it's just NBOW. In the notes section is where you add relief. So I'll show you at the bottom of the code file, we have a notes section, and you can see that we have all of the different levels of relief. However, open water, it isn't necessary to put a level of relief. So for this, we just leave it empty. This is only relevant when there is actually a relief feature. Okay, so we're just going to work through our points now, and you will see that it's very simple once you know your codes, and you can just use your keyboard and the tab key to shift between the different cells. So it can get quite quick to do this. At G, we have a very different situation. So the dominant feature near point G isn't open water, but rather this coral. So you will have to identify this coral using a range of guides, and then determine which category it falls under in the Katami classification scheme. You can then go to your code file and find the code for this coral. So I'm calling it a staghorn coral, and I know that that's within the Cnidarian stony corals, and you can see there's lots of different types and morphologies, and there's ours, and the code is CSST. So we'll place that in the ID cell next to the point G. Okay, so obviously there is relief here, and I would say that is good relief that is offered by this coral. So we will be adding a code in the notes section next to G, and we just go down to our notes section in our code file and read through the different relief levels. I would say it's good relief, about over 45% in slope. If we go to relief level 4, it's speaking of vertical walls, so it's not that high. So relief level 3, I would rather go with than the others. So there is some subjectivity, so it's important to meet with your research group and make sure that everyone's on the same page when analyzing and learning how to do these descriptions. Okay, so then you're going to work through all of your other points. I'm just going to try to jump through this video without causing too much trouble. So we go through all of it. You can see that for the bait canister, point B lands on the bait canister. So what we do is we just use a dummy variable like shadow, and that just won't be included in the analyses. And we obviously don't give it a level of relief. So once we have worked our way all the way to the 35th point, which is I, we can then ensure that we have described every single point, and then you want to save your work. So the first thing, you want to save image with points, and you want to save it in your dated subfolder, and you can call it the same name as your sample code. And you can see that this is actually a BMP, not a JPEG. Again, you can refer to the top of your CPCE file. Okay, and if you go open this, you can see what is being saved. So you have your JPEG, but you also have your BMP. And the BMP is the JPEG basically, so it's the image, but with the points overlaid. And this can be very useful for quality control once you have your data exported. So if there's errors or anything suspicious, you can quickly come back and check what it was originally identified as. Then you want to go to your little blue disk, I don't know if you can see it there, and click Save. That will save your CPC file for this habitat image. So you just want to quickly locate your master folder that you're working in and the dated subfolder, and you want to save your CPC file as the sample code. Okay, if you want to move to the next picture, you would just press the little arrows. Okay, so if we are exporting our data, the most important thing to ensure is that you have all of your habitat images, your code file, and the CPC files all saved within a single subfolder. And this is important with CPC, especially when code files have been updated during a project analysis phase. So this is just an SOP that we follow with the file management because we find it easier to work this way. Okay, so you will export one dated subfolder at a time and then later merge all the data together. Just moving through this quickly. Okay, so in your CPC, you go to File, and if you would want to view or do some final edits to your images, you could go to View, Edit Multiple CPC Files. For today, we are exporting our data from our CPC files, so instead we are going up to Save. Save CPC files to Excel. You want to close any Excel files that are currently being in use. And then you want to locate the D drive or the C drive in which your master folder is saved, and then locate the subfolder which you are wanting to export. Double click on it so that all of your CPC files copy across and are highlighted in the right-hand window. And then you are going to click at the bottom, New Excel Workbook. Okay, for the transect name, you can simply just add the date of the dated subfolder that you are exporting. On the right-hand side, you want to click Database Friendly Columns. And you want to click Override Code File Directory Location, just to make sure that you are using the correct code file. So that would be in your master folder, in the dated subfolder that you're exporting. Okay, and then you want to press Process Files. And it is now going to run through, and then you're going to specify the Excel format that you would prefer. Okay, it's going to run through the processing, and it will automatically give you the location where you want to save it. We just save it as the date with an appropriate name in the dated subfolder and press Save. Okay. If you open up your data subfolder, you will find your Excel workbook there. And you can see that it has multiple different sheets. At our platform, we tend to use the archive sheet as it is easiest to work with, and it comes out in a very similar format to our max in and length data that is shared, exported by Event Measure software. All of the empty files are basically just what we didn't enter in the point header information, but here you can see all of the different classifications have been recorded, and it records the different JPEG files that you use so that you can always refer back to them, as well as your relief. Okay, and your samples are as rows. Okay, so some tips: always have your resources available, such as the Katami visual guide and other benthic invertebrate guides available. It's important to know the depth and region of your habitat images so that you can accurately identify. Although as a beginner you are still learning, code knowledge can be very useful. It can make this process a lot quicker for you. And improving the image quality by having the video open so that you can play the video and see how the different features move can be very helpful when identifying, as well as using the tools in CPCE for image enhancement. Troubleshooting in CPCE is something that I turn to the manual for. This is available online. The solutions can often be quite interesting. So for like runtime error 13, that is just simply a control panel setting that you have to change. So this manual can be very helpful for that. Okay, so lastly, I'm just going to be working through our quality assurance and quality control standard operating procedures. And this is going to be quite a quick run through, so please bear with me. So our approach is also based on that of Langlois, with a few modifications to suit our platform as well as our certain project needs. The quality assurance and quality control is done by an experienced analyst called the controller, and it should be done according to standard operating procedures, pre-processing, during the processing, and also post-video processing. In addition to this, any changes, any errors, any updates made should all be recorded in a template sheet, which I'll give you a bit more information on now. Okay, so before processing, the quality controller can try to prevent errors by just training the analysts in the software, training them according to SOPs, exposing them to guides and resources, and constantly checking in to detect errors early on. It's also quite beneficial to build a reference library of BRUV's images, and these can be used in combination with guides and other resources. In addition to this, it's important for the controller to provide standardized and up-to-date files. And when I say files, I mean the species or habitat code files, SOPs and templates, and these should be shared with all the analysts and regularly updated. So quality control that occurs during the processing, obviously it's more comprehensive, but again, this is the basics. So in our standardized folder system that I haven't actually gone into in too much detail, we have two folders called the Can't ID folder and the Confirm ID folder. And during the video analysis, the analyst is able to extract habitat images or fish species images and save them in either the Can't ID folder or the Confirm ID folder. The controller can then go and look at these images, confirm the IDs, and this can help feed the reference library that I spoke about earlier. Okay, post-processing, so this is once the EMOBs have been created for all the samples, the controller should work through about 10% of the EMOBs, and based on the number of errors, make a decision to either ask the analyst to redo the EMOBs or to get more training and redo the EMOBs, or continue, and if it's a reasonable amount of error. So basically for beginners, we allow 60% minimum error. whereas for more experienced analysts, we allow 30%. So basically the controller should work through all the EMOBs, attend to all the comments, and check for any ID errors, max n count errors, length inaccuracies, incorrect setup of EMOBs, and incomplete information fields. The controller should also work through the exported data, so the Excel file. Using all the different Excel formulae, you can locate and identify any spelling errors, any outdated species names, incomplete fields, or data entry errors. Lastly, the controller should record all error and update the details. So we have a template Excel file for this, and it ensures that all the details of the sample are recorded. It also includes all the error details and reasoning why it was an error so that the analyst can learn from it. And it also includes details of the QA/QC so that it can be referred back to one day. Okay, I've added some useful resource links here. However, I am going to share in the chat group a little bit of a quick guide and a summary, and it will include all the useful references and resources that I have mentioned today. Thank you so much for your time, and I hope you enjoyed that talk.
Thank you very much, Roxanne. A lot of work goes into that, and attention to detail obviously really needs to take place at every single step. So lots of admiration for the work that you're doing. I have a question for you. Is the event measure software valuable for analyzing the mono BRUV videos as well as the stereo BRUVs?
The event measure software is definitely going to make the process a lot more efficient. And like I said, when you are using free alternatives or any media player that you can step by step through the frames, it's absolutely possible, and you can get the exact same abundance data out. But there obviously is a higher chance of data entry errors. Something like what we saw yesterday, Beagle, I'd consider before purchasing, something like event measure if you are only using mono BRUVs. But we definitely, when we are analyzing, we definitely try to get an event measure key to our analysts to make it all go a lot quicker. It still takes a lot of time, even with event measure.
Great, thank you. And just following on from that, with this processing, there's a lot of Excel spreadsheets, it seems, that comes through. Have you got a system in place for kind of collating those Excel sheets? I'm not sure, does the data need to be appended to one another? And if so, do you use another databasing system at all, or do you leave them in the separate Excel sheets?
Yes, so that's why, the quality control afterwards is very important, especially on the exported data. I kept mentioning the sample code. That's a standardized code that links the number of the sample, the date, and the region that the field trip took place in. And that sample code can link all of those tables together. And that's basically how we managed to merge them all. But that said, we do tend to keep them separate as a metadata Excel sheet and a max n data sheet, a length data sheet, and then also one for habitat data. But a bit later, we're going to be hearing about how we do store our data sets, how we archive them, and that's from Willem's talk. And then you'll be able to hear a bit more about how we do that and how we, work, find different pieces of data and link them all together.
Oh, wonderful. Now that will be very useful. And then another one from me, in terms of this processing of the data and the entering of the data, you also obviously needed to learn this process. What are some of your personal sort of tips for working through this? And And yeah, just some advice for those listening about how to get started, because even for myself, you know, it can seem quite overwhelming at first, you know, to learn these new programs, and maybe that puts some people off, you know, but you know, so have you got any tips for those that are wanting to start something like this, you know, and what should they do, and how best to get started?
Yeah, it is definitely overwhelming at first. It still is. I'm still beginning with the habitat images now, and I still find it quite challenging. And you tend to second guess yourself a lot. So having, you know, a lot of support in your research group is very helpful, especially to just, you know, have that one person that's a bit more experienced than you to rely on. We were very fortunate with Dr. Anthony Bernard. He's always available and willing. And I think for me, the main tip would be, you know, when you do run into trouble, ask early rather than later on once the data's all been done. So if you have an ID issue or a software issue, we rely heavily on WhatsApp, and we find out in real time so that the error doesn't carry on throughout the data, and then turning back and trying to update EMOBs, that's where it becomes a bit time consuming. But also just having this quality control in place, you know, having these SOPs in place, because even the most experienced analyst can make errors, and we do find errors, you know, every single time. So having some sort of QA/QC SOP in place is definitely helpful.
Oh, fantastic. Thank you so much once again for a fantastic presentation and for all the hard work that you're doing. We're going to move on to a poll now. So up on your screens, you should be able to see another poll. Please take the time and fill that in. And in a few minutes, I'll be handing over to the next chair. So don't go away. We're going to continue with session 6. And I'll briefly just introduce Lauren, who will be taking us into the next chairing session. So please go ahead and fill in that poll. Okay, great. So I'm going to be handing over to Lauren Williams, who will be